All right, Math A honors, we're getting into lesson 6.2a. Activity 1. Blows an image of a rectangle which is 3 units by 6 units. On the first grid provided, draw a rectangle with side lengths 3 times as long as the image. Label the corresponding vertices Q, R, S, T. And on the other grid, draw a rectangle with side 1/3 as long as the image. Label the corresponding vertices U, V, W, X. So to do this, I first look, this is obviously the 3, and this over here is the 6. So if I want to make it 3 times as big, I need to multiply. That's my scale factor. I'm going to multiply. So my 3 times 3 is 9, and my 6 times 3 is 18. So I need to make it 9 by 18, which means it's going to be pretty large. So I'm going to start in that bottom corner and build it up. I'm going to go ahead and use my line tool. All right, so starting in this bottom corner, I need to go over 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Good. And then I need to draw a line going up 18. I don't know if I picked the line tool. I think I picked the rectangle tool on accident. That's okay. It'll work out.
Yes, it will.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18.
Infinity.
I have my peanut gallery in the back, my daughter. All right.
And not a peanut gallery.
I'm going to finish off my rectangle.
Your rectangle.
At least twice. Okay, then I have to be careful. It says to name the corresponding labels. So here, we're going to assume it's going alphabetically, M-N-O-P. So I need to go from the bottom corner, I need to go clockwise. So this would be my Q, this would be my R, this would be my S, and this would be my T. On the other one, I'm doing a 1/3 as long as the original. So go ahead and pause the video and draw one that is a 1/3 and label it up corresponding. All right, this time you should have drawn a little baby rectangle that's 1 by 2 with U, V, W, and X. Now what we're going to do is we're going to be looking at as you change the sides, what happens to the change in the perimeter and the change in the area. So I need to go calculate the area and the perimeter for both of these. So here, perimeter is when we add all the sides up. So on my perimeter on this one, I have to go 9 plus 18 plus 9 plus 18. And when I do that, I get a perimeter of 54 units squared. Area, I have to go base times height, so 9 times 18. When I do that, I get 162. I'm sorry, that last one should have just been units because it's a length. This one should be units squared. So we need to find the perimeter and the area for the original and for the little one. So go ahead and pause the video and find the perimeter and the area of those, and then fill that information into our first half of the chart. All right, so for the original one, it should have a perimeter of 18 and an area of 18. For your enlarged one, you should have a perimeter of 54 and an area of 162. And for the reduced one, you should have a perimeter of 6 and an area of 2. Now here, this just says same because we didn't change it from the original on the first one, but now we're looking at what happened from the original to the second one. So we see on our original to our second one, on our dimensions, we scaled up by a factor of 3. We made all the sides 3 times as big. When we did that, the perimeter also became 3 times as big. But the area became 9 times as big. If we look from the original to the reduced one, here we made it 1/3 as big. The perimeter became 1/3 as big, but the area became 1/9 as big. Okay? So here, when we're changing the dimensions, we're talking about the scale factor. What did you multiply by to enlarge it, or what fraction did you multiply by it to reduce? That is the scale factor. Okay? The perimeter ratio is how are the perimeters changed? So this is the perimeter ratio. And then over here, we were looking at the change in the area, or the area ratio. And one thing that we should be seeing is that when I have a certain scale factor, whatever it happens to be, my scale factor is A to B, could be 3/1 or 1/3 or 2/5, whatever it happens to be, my perimeter ratio is also the same. Okay, so if you multiplied the sides, well, then all you're doing is also multiplying the perimeter, because you just made each of the things that you're adding up 3 times as big. So effectively, you made the sum 3 times as big. But when you have the area, you are taking the scale factor, your area ratio, you're taking the scale factor and you are squaring it. You get a squared to b squared. So if it was 3 times as big, the area is going to be 3 squared, 9 times as big. If it was 1/3 as big, the area is going to be 1/9 as big, 1/3 squared. Because what's essentially happening is you took my numbers here, 6 times 3, and I multiplied this one by 3, and I multiplied this one by 3. So I have an extra 3 times 3, which is effectively 9 times as big. Okay? You affected both of the dimensions which you're about to multiply, so you are squaring your change. All right, so we have to realize we have to work between our areas and our perimeters. So we have to remember that perimeter is the distance around the shape, and area is the number of square units in a shape. A rectangle has a perimeter of 148.6 meters and a width of 29.2 meters. Find the area of the rectangle. So visually, if I have a rectangle, this is my width and my length. It doesn't matter which one you call the width and which one you call the length. In my perimeter, I have to add all the sides, so I have 2 widths plus 2 lengths. Area is the width times the length. So now I'm going to fill in my information. I knew by reading the problem I had a perimeter area problem for my rectangle. I know my basic formulas. Now I plug it in. So I have 148.6 is equal to 2 times 29.2 plus 2 lengths. I don't know what the lengths are. And so far for the area, I have a width of 29.2, and I don't know what the length is. So over here, I have one variable. I can solve it if I just have one variable. Over here, I have 2 variables. So I can't start with the area equation first. I've got to start with the perimeter equation first and work it out. All right, here we go. 2 times 29.2. I get 148.6 is equal to 58.4 plus 2 lengths. I want to isolate the variable term, so I'm going to subtract 148.6 minus 58.4. All right, so I get 90.2 is equal to 2 lengths. Now I want to get the variable by itself, so I'm going to have to divide by 2. And I get the length is 45.1 meters. Then I can go ahead and plug it into this formula. Area is equal to 29.2 times 45.1. So then I can multiply them together. And I get that my area is 1,316.92 meters squared. All right. Now you, with your partners, are going to pause the video and try number 3, 4, 5, and 6, and then in 5 minutes, come back and check your answers. All right, check your work. So when you triple the dimensions, you are making the area 3 squared or 9 times as large. So I don't have to sit there and actually change the side lengths I had up there. I can just take the area answer and multiply it by 9. And when I do that, I get 11,852.28 square meters. Number 4, we had to pay attention that it was a square. A square has all sides congruent. So the perimeter is a side plus a side plus a side plus a side, or 4 times the side. So 60 equals 4 times the side. Divide by 4. The side is equal to 15 meters. The area, I have to go the side times the side, or side squared. And 15 times 15 is 225. So the area is 225 meters squared. What if the area was a quarter of the size? Well, if the area is a quarter of the size, then the scale factor would have to be a half, because a half times a half is a fourth, and the scale factor squares the area. So I know that the sides would have to be half the length, or 7.5. Number 6, a little bit tricky. It's tricky because it's not in the same units, and we need to pay attention to units. This is in inches, and this is in square feet. So we have tiny tiles that are going on a very big rectangular square. This is 12 feet by 21 feet. You do not have a huge tile. This does not say a 9 foot by 9 foot tile. That is not what that says. It says a 9 inch. So I got to get into the same units. All right. So 9 inches. A foot is 12. So 9 inches is equal to 9/12 or 3/4 or 0.75 feet. So we're putting these tiny little tiles that are 0.75 times 0.75. Okay? So I have to think. My big area is 12 times 21 feet squared. 12 times 21, 252 feet squared. And I'm covering it with little tiles that are 3/4 by 3/4. 9/16 or 0.5625 feet squared. So when we divide those numbers, we can figure out how many tiles we actually need. And we get that we're going to need 448 square tiles. You will need 448 square tiles to cover the floor. Okay, if you have to go back and correct your work, go ahead and pause the video. All right, so we've been dealing with rectangles. Now we're going to do the same thing, and we're going to deal with a triangle. Below is an image of triangle ABC. On the first grid, draw a triangle with sides lengths twice as long as the image. Label the corresponding vertices D, E, F. On the other grid, draw a triangle with lengths half as long as the image. Now, I don't want to sit there and measure my base is easy to count, but my ones that are not lining up on the grid are not easy to count. But we don't even need to worry about it. What we need to worry about is the base and the height. Whenever you have a triangle, you need to pay attention to the base and the height. Okay, so it doesn't matter which one you call a base. You really could call any one the base. Of course, on this one, it is easier if you call the one that you can count the base. The height is from the opposite vertex down. That would be the height or the altitude. Okay, so we need to pay attention to those dimensions. So my whole base is 1, 2, 3, 4, 5, 6, 7, 8. And my height is 1, 2, 3, 4. As well as that, I need to pay attention to how the base is being split. Okay, so this whole thing is 8, but it's being split into 2 and 6, where this is still a 4. Those are the things that I need to pay attention to when I am building my new rectangle, my new triangle. I don't really need to pay attention to those two sides that are not the base. Okay, so twice as long. My base is going to have to be 16, and my height is going to have to be 8. So again, I go ahead on the bottom, I use my little line tool, and I go 16 across. I'm going to start the corner because 16 is kind of a big number for this grid. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Oh, good guess. Okay. Okay, I need to cut the base proportionally. Oh no, module 5 is coming back at me. Proportionally, so instead of 2, 6, I'm multiplying by 2. It's now going to be 4, 12. So 1, 2, 3, 4. That's where the altitude hits. Okay, I'm going up twice as high, so I'm going up 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, again, I counted. This is not really a part that we're drawing. I'm making it dashed because that's what I counted. And then I go ahead and I connect my other sides of the triangle to that vertex. Okay, so when you're busting out similar triangles, you want to pay attention to the base and the height. All right, and then we're naming it corresponding. So it was A, B, C going counterclockwise. So D, E, F.
Don't start yet.
All right, so the next one, you want to make it half as big. So go ahead and try that and then check if you did it right. All right, so here you should have a smaller triangle. It has a base of 4. The altitude cuts it 1 in, leaves 3 left over, and goes up 2. Okay, so we're just describing what we did. I paid attention to the length of the base and height. And how the height proportionally cuts the base. All right, do you think the angles of the new triangle are the same or different? So I really could take this little triangle and I could line it up within this triangle. I could come over here And I can go over 1 up 2 and put my line tool. If I grab my line tool, that would be helpful. Make it orange. I can place that right over here. Okay, and I see that these are parallel. So this angle shared the same, and these two angles are slanted. This side is slanted in the same manner as this side. So actually the angles are exactly the same. So when we enlarge or reduce a triangular shape, we are not changing the angles. We are only changing the sides. The triangles are similar. So the angles, corresponding angles have the same measure. All right, moving on to activity 3. We will now explore the relationship between two triangles that have the same angle measures, but the side lengths are different. So these are similar triangles. So here I see that I have 15s both in the bottom corner, and then I have that 117 up in the upper left corner, and then I have the 48 up in the upper right corner. So I see that all the angles are congruent. So I have similar triangles. PRQ, a squiggle is a similar symbol. I have to go in the same corresponding order. So I went 15, 117, 48. I got to do the same way over here. So 15, 117, 48 would be A, C, B. So it doesn't matter how you write the first one, but the next one has to be corresponding. Okay? So angle P corresponds to angle A, and we can actually say they're congruent. Let's make it easier. Angle P is congruent, equal with the squiggle on top, to angle A. Angle R is congruent to angle C. Angle Q is congruent to angle B. Now the sides are not congruent. The sides are proportional. So if I put on the bottom of my length PR, length RQ, length QP, okay? I know that from the other triangle, PR corresponds with AC, and RQ corresponds with CB, and QP is corresponding with BA. Okay, if I actually took their measurements, AC 6/18, CB 2/6, BA 7/21. All of these are equal because they all reduce to 1/3. If I want to go from this upper triangle to this lower triangle, I would have to multiply by 1/3. If I wanted to go the other way, I would have to multiply all the sides by 3. So describe how they are similar. Triangle PRQ is 3 times as big as triangle ACB. Okay. How are the triangles similar? How are they different? The corresponding angles are congruent. the corresponding sides are proportional. What do you know about the lengths of the sides of the two triangles? Same thing we said here. You can actually just move this down. Triangle PQR is 3 times as big as triangle ACB. All right, so 2 more definitions to go. Similar figures. Similar figures have corresponding congruent angles the same kind of shape. So if I'm saying like 2 rectangles or 2 triangles or 2, that would be the same kind of shape with corresponding congruent angles. And corresponding proportional sides. Okay, so if I say triangle ABC is similar to triangle DEF, and I draw ABC in this kind of manner, then I'm going to make DEF a little smaller. Okay, I would know that I'm pretending both right angles. Those 2 angles would match up. And A would have to correspond to D. And C would have to correspond to F. And if I called this a, let's say, a 6, 8, 10 triangle, maybe this one would be half as small. Maybe it's a 3, 4, 5 triangle. Okay, all the sides would be reduced by the same multiple. Okay, corresponding parts, remember, are things that are in the same spot when you oriented the shape the same way. So A is lining up with D, B is lining up with E, and C is lining up with F. When 2 shapes are oriented the same way, they're twisted, they're flipped the same way. Corresponding parts are in the same location. Okay, so there's no shorthand for that, but just looking at what we did before. Angle A corresponded to angle D, and angle B corresponded and was congruent to angle E, and angle C corresponded and was congruent to angle F. If I built this, AB on the bottom of my fraction, AC and BC, I would write my ratios where they line up. So AB is lining up with DE, AC is lining up with DF, and BC is lining up with EF. Okay, that's the end of the lesson. Go ahead and hit save.